Good morning. Good morning to everyone. Okay. So what I will do is I will brief about the yesterday's class. Now all of us we know in yesterday's class we have discussed about F block elements, right? So we have discussed about F block elements. Now when I am talking about F block, what is the another name for these group elements? They are called as inner transition elements, right? Inner transition elements. That's where we have the another name for this particular group. So inner transition elements. Very good. So you people are right. Gahan has told inner transition element. Yes, absolutely correct. Now why they are called as inner transition elements? That is because in them n minus 2 F subshell will be getting filled up. N minus 2 subshell will be getting filled up. So what is N? N is the outermost energy level value, right? Where N is the outermost energy level value or valence shell. Outermost shell number. So that's where we have the N minus 2 F subshell is getting filled up. Therefore they are called as inner transition elements. Fine. Now when it comes to inner transition elements, we have two types. One is lanthanoid series and another one is actinoid series. So we have two types, lanthanoid series and actinoid series. So why they are called as lanthanoid? Because they comes after lanthanum. So why they are called as actinoid? Because they comes after actinium. So that's where we have the lanthanoid series and actinoid series. So where lanthanoid series starts from cerium. Where lanthanoid series starts from cerium. Now from here it will go up to lutetium. From here it will go up to lutetium. When it comes to actinoid series, it starts from thorium. So thorium to Laurasium. So thorium to Laurasium. That's where we have the elements which belongs to lanthanoid series and actinoid series. So in that case, yes, Shri Vidya, absolutely correct. So when it comes to lanthanoid series, so this is actually period number 6. This is actually period number 7. Now, when it comes to these elements, they are present between group 3rd and group 4 because they after starting of the group 3rd, that is lanthanum and actinium. So after those elements, these series will start. So lanthanum and actinium, they belongs to group 3. So therefore, these elements, F block elements, they are present between group 3 and group 4. Exactly we cannot tell to which group because they have not given any name to this group. So that's where they are present between group 3 and group 4. All of you have understood? Now, what is the general electronic configuration? Outermost general electronic configuration. Can anyone? What is the general outermost electronic configuration? Can anyone write? General outermost electronic configuration for inner transition elements. So it will be N minus 2 F 1 to 40, N minus 1 D, N minus 1 D, where we can write 0 to 2, then NS2, then NS2, right? So that's where we have the general outer electronic configuration for inner transition elements. Fine? All of you have understood? This is what we have discussed in the last class. So this is what we have discussed in the last class, that is related to F block elements. Now when it comes to F block elements, why they are present at the bottom of the periodic table? That is just to maintain the uniformity of the D block elements. Otherwise what will happen? Even D block elements will get disturbed. I am talking about arrangement in the periodic table. So not to disturb the D block elements. So therefore all the F block elements have been shifted to bottom of the periodic table. Fine? All of you have understood? So that's why inner transition elements which we have discussed. So how many elements will be there? In the lanthanoid series 14 elements and in actinoid series 14 elements. Total 28. We have the inner transition elements. Okay? Now what is the speciality of the actinoid series? Actinoid series, almost all the elements are radioactive. That's where we have the transuranium. That's where we have the transuranium. So what is transuranium? So transuranium means these are the elements which comes after the uranium. They are called as transuranium elements, and all of them they are radioactive. And uranium belongs to actinoid series, and uranium itself is a radioactive element, right? Then we have discussed about how to write the nomenclature, IUPAC nomenclature for the elements. Numbering based on the number 101, 102. I am talking about those elements having atomic number greater than 100. Official name they have given, but with number only we can give with number. Okay, Ashish Joseph. Atomic number of uranium, it should be 92. Atomic number of uranium should be 92. Yeah, it should be 92. Okay, so that's where we have the uranium 92. Molar mass, atomic mass will be somewhere around 236. Okay, but exact this one I don't remember. I think 236 only. So that's where uranium we have. Fine? All of you have understood? Now that's where we have the 92. 92 atomic number. So atomic mass should be somewhere around 236, if I am right. 236. So that's where we have the uranium. Fine? All of you have understood, and all of us we know this uranium, it is going to emit the alpha radiation. Gahan. Okay, 238. Gahan is telling it should be 238. Fine. So that's where we have the uranium which is going to emit the alpha radiation. Fine. So it will emit the alpha radiation. Okay, anyway, we will not go in detail, but that's where we have the actinoid series. Most of them they will be radioactive elements. Fine. Shall we move to the next one? So that is with respect to atomic number greater than 100. What can be the name of the molecules or elements which are present having atomic number greater than 100? And in your periodic table they have given 3-word abbreviations, right? So that's all because of the nil, all like that it will come. At the end it should end up with IUM. That is compulsion. Say for example I have 107. So I can call it as nilheptium. anil heptium. Fine. But we have official name also, but this can be another way of naming the elements. Because some of the elements, now we know up to 180n elements, now we know it is characterized. But before that, they were not knowing. But still they have kept this place in the periodic table. So to keep it empty, they have mentioned the name. So that's where we have the anil heptium. Somewhere we have written S, it should be heptium. Okay? So that's where we have the molecule. Okay? All of you have understood? Any doubts? Any doubts? Yeah, 7 is septum. Okay, I wrote heptium. Okay. Sorry. Anil septium. Yeah, correct. So I wrote heptium. Okay, fine. It was a mistake. It should be septium. Yes, 7 is septum. Okay, so fine. So in that case, yes, anil septium. If it is 8, anil octium. Fine. If it is 117, then it can be, yes, you people are right, it should be septium. I have written heptium. So it should be unseptium. It should be unseptium. Okay? So that's where, yes, absolutely correct. So that's where we can name the molecule. Now they have given official name also. But official name, they will not ask. Normally they have not asked, but they will ask this one, IUPAC nomenclature. Fine. So now, when it comes to 1 mark question, you can expect from this particular part. Okay. But otherwise, official name will be either it can be based on scientist, or it can be based on the city where it has been discovered, or it can be based on the laboratory where it has been discovered. So there are different namings. Fine. So that is called as official name. But this is where IUPAC nomenclature. This one they will ask. Okay. So then we have discussed about based on the atomic size. See, the question can be explain the arrangement of elements in the periodic table. I am writing PT. So it should be periodic table. In the periodic table based on the atomic size. This will be the question. 2 marks question. You imagine this one they have asked. This can be the question. 2 marks question. Now it's very simple. Just you should tell that what will happen across the period and what will happen down the group. So the answer for this one will be in the periodic table across the period. In the periodic table across the period, atomic size will, anyone, atomic size will decreases. Yes, atomic size will decrease. And second point, and down the group, atomic size will increase. That's what we have discussed in the last class, right? So across the period, atomic size will decrease, and down the group, atomic size will increase. All of you have understood? So that's where we have the arrangement of the elements in the periodic table based on the atomic size. Fine. Now this is one sentence. Question is for 2 marks. But normally you will get the marks for this. To be on safer side, we can tell or we can give the reason. This is because what you are going to write? So this is because across the period, electrons will be entering into the same energy level. Right? This is because across the period, electrons will be entering to same energy level. And down the group, electrons will enter into the next energy level. Down the group, electrons will enter to next energy level. That's where we have the reason. Right? So therefore, there will be increasing in the atomic size down the group because electrons are entering into the next energy level. Right? So that's where we have the reasons also. Now, no doubt, no one can deduct the marks. They have to give the complete marks to you. Fine? Even if you write this one in the periodic table across the period, atomic size will decrease 1 point. Second point is, down the group in the periodic table, atomic size will increase. Done. 2 marks will be given to you. So this is reason, second point. In this case, whatever next sentence I have written, it is the reason for this particular arrangement. All of you have understood? So that's where we have the answer for this. Fine? All of you have understood? Now, if you understand how exactly elements are arranged based on their atomic size in the periodic table, naturally elements are arranged based on their atomic number, no doubt. But during that time, due to the atomic number is getting increased, due to the entry of electrons to energy level, in some cases there will be contraction of energy level, in some cases there will be expansion, right? That is going to affect the atomic size. Fine? Now, before coming to that, Anush, before going for that, another very important one is that now we have atomic radius. Now we have the atomic radius. Then we have the ionic radius. Then we have the van der Waals radius. Now, when I am talking about van der Waals force, which you people are going to study in your states of matter in first PU only, we have one of the topic which is called as states of matter, where you are going to discuss about van der Waals force in detail. Now I will tell that one briefly. Okay. Now, when I am talking about atomic radius, so naturally, I have, for example, fluorine. In the nature, halogens, they are present as diatomic molecules. Halogens will be present as diatomic molecules, just like oxygen, O2. Same way, halogens will be present in the diatomic form. Okay? Darshan, I will come to that. So that's where we have the fluorine, F2. Now, what do you mean by F2? Where two fluorine atoms, they are in the covalent bond with each other. They are making the covalent bond with each other. That's where we can write it as F. Alright? And if I take this one from nucleus to this nucleus, so that is internuclear distance. That is nothing but internuclear distance. I have shown it as overlapping because in a covalent bond there will be overlapping of the orbitals. Okay, that's why I have shown. Otherwise, you can simply write it like this also, no doubt. You can simply write like this also, no problem. Fine. Now, when I am talking about atomic radius, it is nothing but a distance between these two and divided by 2. Half of the distance. Right? Because here we can clearly see. So atomic radius means this is the one which is called as atomic radius. Right? So distance from the nucleus to the periphery of the atom. That is nothing but atomic radius. Fine. Now when I am talking about atomic radius, what I want people to understand here is, when we are talking about atomic radius, we are dealing with the covalent bond. Covalent bond containing molecules. Fine. So now based on this we can have the atomic radius of fluorine. If I take Cl2, chlorine, then I can have the atomic radius of chlorine. Fine. So that is one thing. That is one concept. Now if I take iron, in the nature, iron will be present with metallic bonds. They are going to make the metallic bonds with each other. If I take iron rod, it is having metallic bond character. Anyway, in detail, in chemical bonding you people are going to discuss, and in second year, once again, solid state you people are going to discuss. So what I mean to tell here is, iron is not having a covalent bond, it is having metallic bond. It is having a metallic bond. Once again, atomic radius of iron can be calculated by the half of the distance of the metallic bond. Half of the distance of the metallic bond. So that's where we have the atomic radius. Any doubts? That's where we have the atomic radius. For most of the element, 90% of the elements in the periodic table, we can go with the atomic radius, where these elements will have either metallic bond or they can have the covalent bond. Therefore, we can go with the atomic radius to express the atomic size. In your exam, they will ask, explain the arrangement of elements in the periodic table based on the atomic radius. Then you should not scold. Hey, Raghavendra sir, adeno pata madrappa. Atomic radius ಬಗ್ಗೆ ಹೇಳಿಲ್ಲ. Sir has told about atomic size. So one and all same. Okay, one and all it is same. Now, when I am talking about ionic radius, this is bit important for your exam point of view and even competitive exam point of view. Ionic radius. Fine. Now, when I am talking about ionic radius, see for example, already we know that sodium is going to donate the electron and it will become Na+. Naturally, in both the cases, atomic number is constant. There is no change in the atomic number. Only number of electron got decreased. Here it was 11 electron, here it is 10 electron. So it's due to the number of proton which has increased by 1. We have indicated it by +1. Fine. So where this electron has been taken? It is taken by the chlorine. So which has become chloride. Now, atomic number of chlorine is 70. So here also it is 70. There is no change in the atomic number. It is remaining as 70. That means here it is 17 electron, but here it is 18 electron. So one electron is more, which is denoted by minus charge. Okay? All of you have understood? Fine. Now we have an atom. Now we have an atom. Right? So where electrons will be present in the outermost shell, even inner shell it will be present, but I am focusing on outer electrons. Or if you take all the electrons, there will be presence of nuclear force acting on these electrons. There will be presence of nuclear force which will be acting on these electrons. In atomic structure, you people know. Sir, if there is an affinity between proton, that is nucleus, and the electron, why the hell electron is not falling to the nucleus? That one all of you have got the answer. That is because electrons are not static. They are revolving. They are revolving around the nucleus. If they would have become static, there is a chance or there is compulsion that this electron will fall into the nucleus. Atoms will going to be destroyed, right? But that is not happening. Atoms are stable. That's what you people have studied in your atomic structure topic. Now, there is a nuclear force which is acting on the electrons, right? Now, in one case, what is happening? Nuclear force is remaining same, but number of electrons are getting decreased. Now, if I take this one, first one as the condition, where nuclear force is dominating. Nuclear force is dominating over the number of electrons. Nuclear force is dominating over the number of electrons, right? If I take the bottom one with respect to chlorine, it is reverse. Here, number of electrons are dominating. Number of electrons are dominating over to nuclear force. All of you are understanding? It's very clear. If you have doubt, you can ask. What I mean to tell you is, when I am talking about sodium getting converted into Na plus, number of proton 11, number of proton 11, number of electron 11 electron, number of electron 10 electron. So what is happening? Since number of proton is constant, it's dominating over the number of electron, right? So due to that, what will happen here is, since sodium belongs to period 3, I am showing 3 energy level. Okay? Now, when it will become Na+, what is happening? There is a decrease in the atomic radius because nuclear force is same. Please remember, there is no electron in period number 3. That means outermost energy level has been removed. Still, I have shown to make sure that there is a decrease in the atomic size. There will be contraction. Of shell will take place because nuclear force is dominating over the number of electrons. That's what we can observe. Fine. Now exactly reverse. When it comes to chlorine also belongs to period number 3, right? So therefore, if I take, this is the atomic size of the chlorine, which has to be smaller than that of the sodium. Now when it comes to chloride, due to number of electron which is dominating over the number of protons, so therefore there will be expansion. Of the outermost shell, or I can tell there will be expansion of the energy levels. So due to that, atomic radius is going to increase. All of you have understood? So that's where we have the ionic radius. Here it is atomic radius, but here it will become ionic radius. So please remember, anions, that means negatively charged ions, right? So anions will have larger size, or larger radius compared to parental atom. Fine. So exactly reverse for the cations. which are positively charged. Cations will have smaller size. Will have smaller size compared to parental atom. Compared to parental atom. So that's what we can say here. Sodium is having larger radius compared to Na plus, right? Sodium is having larger radius compared to Na plus, and chlorine is having smaller radius compared to chloride. All of you have understood? Any doubts? Any doubts you people have? That means as there is an increase in the positive charge, atomic radius, or that is ionic radius, is going to decrease. As there is an increase in the negative charge, once again there will be increasing in the atomic radius. Fine? Okay? So here it is only one positive and one negative charge, but that is not universal. We have some of the elements which can have more than one positive charge and more than one negative charge. So in that case, as the number of charge will get increased, same thing will happen with respect to that atomic radius, that is ionic radius. Okay? Fine? So that's where this is bit important for your board exam also and even for your competitive exam also, because they will give some questions like arrange the following elements based on their size, based on their atomic size, and they will give the elements. So either they will ask increasing order or decreasing order. So that's how you have to arrange. Fine? So this can be 1 mark question for board or competitive exams, many times they have asked. Okay? So one thing is clear. Now, we have group 18 element, which is also called as zeroth group elements. Which are those? Group 18 elements, which are also called as zeroth group elements. Which are those? Which are zeroth group elements? Anyone? Group 18 or zeroth group element? Which are those elements? What the name? Okay, Sri Vidya, she has written, yes, noble gas or inert gas. Right? That's where we have the inert gas. Right? Because of that least reactiveness. Therefore, they are called as inert gas or noble gas. All of you are correct. Now, please remember that whether I am talking about helium or neon or argon or any of these noble gases, all of them, they are present in the nature as in their monoatomic structure, or they are present as monoatomic molecules. Right? Where molecule, actually, what do you mean by molecule? Basic concepts of chemistry people have studied. Molecule means where more than one element are involved. Right? They are called as molecules. Further, it can be classified as compound, where two different elements or more than one element will be involved. Then they are called as compound. Right? Oxygen molecule, that is O2. Fluorine molecule, F2. Oxygen atom, that is O. Fluorine atom, that is F. Right? So, in the nature, almost all the elements, they are present in their molecular form. Right? So, if I take iron rod, where multiple iron atoms, they are present. Right? But when it comes to inert gas, exceptional case. When it comes to inert gas, exceptional case. They are present in their monoatomic form. We don't have He2, this is wrong. We don't have neon 2, this is also wrong. We have in the nature helium. We have in the nature neon gas, that is Ne. Oxygen gas, it is O2. Chlorine gas, it is Cl2. But when I am telling helium gas, then I am talking about He. When I am telling neon gas, then I am talking about Ne. So that's where these inert gases, in the name itself it is there, they are present as a gaseous state in the nature, in elemental form, which is called as elemental form. Now when it comes to helium, monoatomic, what I mean to tell is that inert gases, they are present in their elemental form where they are present as monoatomic condition. Naturally, there is no question of covalent bonds. There is no question of metallic bond, natural. Metallic bond cannot be because they are in the gas, inert gas. So gases cannot have the metallic bond. Covalent bond, no, it is not that because they are present in their monoatomic structure. So that's where we have the van der Waals radius, which is an example for a weak interaction. Which is an example for a weak interaction. We can call it as a non-covalent interaction, very, very weak interaction. Non-covalent interaction, there are many types. In that, van der Waals interaction is one of the example, and which is weakest among the non-covalent interaction. See, for example, if I want to break carbon-carbon bond, if I want to break it, it may demand somewhere around 80 to 100. I will give the approximate value, kilocalories per mole of energy. 80 to 100 kilocalories per mole of energy. That means if I supply this much amount of energy, then only I can separate these two carbons from each other. Okay? So which is called as bond dissociation enthalpy. That means amount of energy required to separate the element which are in covalent bond with each other. Fine? But when I am talking about van der Waals, now see the value. The van der Waals interaction can be separated by merely supplying 1 to 2 kilocalories per mole of energy. Can you compare 100 and 1 to 2? No. Van der Waals interaction is nowhere. If you see the values, then only we can tell. Here it is 100. Here it is approximately 100 times less. So that's where we have the weakest van der Waals interaction. For example, I have one helium here. Okay, I have another helium over here. Now if I want to have the van der Waals radius, then I have to take the internuclear distance. Right? Then it will become van der Waals radius. Internuclear distance between two atoms which are in van der Waals interaction. Then half of those values will give the van der Waals radius. Fine? So that's where we will imagine this is x. X is the value. Now x by 2 will be the van der Waals radius for this particular element. Right? Now if the same molecule would have been with covalent bond, same molecule would have been with covalent bond, whether we can compare between this and this? No. So therefore, please remember, whenever we are talking about inert gas, we are not going to talk about atomic radius, we are not going to talk about ionic radius, we are going to talk about van der Waals radius. Naturally, which will be a bit larger. So therefore, we should not compare the atomic radius of other elements with the inert gas. Because in other elements, we are going with either metallic radius or covalent radius. Right? But when it comes to here, when it comes to inert gas, we are going with the van der Waals bond because they are present in their monoatomic form. Right? So therefore, normally when it comes to atomic radius, in your textbook you can see they will stop at halogens. They are not going to discuss about the inert gas. Fine? Okay? Why that is the case? Because in other elements we are going with either atomic radius or that is atomic radius, where atomic radius will be calculated based on covalent bond or metallic bond. But when it comes to inert gas, it is no covalent, no metallic. It is van der Waals interaction, where van der Waals radius will be there. But otherwise, inert gas should be smaller than that of the other elements, no doubt. Since we are dealing with van der Waals radius in inert gas, it looks big larger value compared to other elements. But still, inert gas will be smaller. But anyway, since we are dealing with atomic radius, we are not going to talk about inert gas. Fine? All of you have understood? So what is happening to the atomic radius, that is atomic size? There will be increasing in the atomic size as you move down the group, and there will be decreasing in the atomic size as you move rightward direction across the periodic table. What about ionic radius? Ionic radius, where cations will be of smaller size compared to their parental atom, and anions will be of larger size compared to their parental atom. All of you have understood? Okay. So next question. Okay. So next question can be, explain the arrangement of elements in the periodic table. Explain the arrangement of elements in the periodic table based on the metallic character, or before that electronegativity. In the periodic table based on the electronegativity. Okay? That will be the question. Now to answer this, first you should define what do you mean by electronegative or electronegativity. What do you mean by electronegativity? Fine. Now, electronegativity means it is the capacity or potential of an element to attract the electron towards itself when they are present in a covalent bond. Anyway, you are going to discuss, no Gahan, it's not to donate the electron, it is to attract the electron. You are talking about electropositivity. I am talking about electronegativity. Okay now? So electropositivity, I will come to that. See, for example, anyway, this one you are going to discuss in your chemical bonding. I have the water, H2O. This is nothing but a water molecule. Now, I can tell that oxygen is electronegative. So due to that, normally we are going to draw the picture like this, right? Where this is the electron belongs to oxygen, this is the electron belongs to hydrogen. So that's where we will show the picture. But in reality, what will happen here is, that's where we have the reality. What is happening? Here, electrons of hydrogen is also pushed towards the oxygen. It's not taken. It is just attracting. Please remember, when I am talking about, okay fine. See here, I have so many pens. That is because Raghavendra sir is having attraction towards the pen. Okay. Now, one beautiful pen is present here. Okay. Now, I am having attraction towards that particular pen. But I have not taken. I am just having the attraction. Right? That is called as electronegativity. I am having the attraction. But if I am taking that pen and I am putting into my shirt, that is called as gaining. So that is called as gaining. Fine. So that's what I wanted to make it clear, Nagesh. It's not the gaining of the electron, it is the attracting the electron. It's not gaining it. Still this electron belongs to hydrogen. Still this electron belongs to hydrogen. Right? Oxygen has not taken it completely. Still, those two electrons belongs to respective hydrogen only. Okay? But still, overall if I see, I can see that electron density is more towards the oxygen compared to hydrogen. Electron density is more towards the oxygen compared to hydrogen. Therefore, we will represent it as delta negative, delta positive. Right? That's what we will represent. Anyway, which is nothing but dipole moment. So I am not going to discuss that one. In chemical bonding, you people are going to discuss. So what I mean to tell you is, if you want to define electronegativity, then you can tell that it is the ability of an element, it is the capacity of an element to attract the electrons or to attract the shared electrons in a covalent bond. Right? So, it is the ability of an element to attract, don't write again, to attract the electrons in a covalent bond. In a covalent bond. That's what we can tell. We can define electronegativity, 1 mark. That's where we can define the electronegativity. 1 mark will be given to you. You know the concept, but I have put the wrong word. I have written gain. Then I will give 0 marks. That's where the difference between attraction and gaining. All of you have understood? Fine. So that's where we have different measurements, different scale. In that, in your syllabus, you have Pauling scale. Pauling scale. A scientist. Okay? So Pauling scale. So according to this, fluorine is having a value of somewhere around 4. Value of somewhere around 4. Then comes the chlorine, which is having value of somewhere around 3. Now, don't think that halogens are the only element which are electronegative. No, it's wrong. Not only halogens, we have some of the elements which are much more electronegative compared to other halogens, except fluorine. Fluorine is a big boss. When it comes to electronegativity, fluorine is considered as a big boss. No one can challenge the fluorine with respect to electronegativity, highest value, that is 4. But if I take oxygen, which is neighbor to the fluorine, it will be having 3.5 Pauling scale, more than that of the chlorine. If I take nitrogen, it is having 3, which is equal to the chlorine. Right? Then comes the bromine, iodine and all, which is somewhere around 2.5 and all, it will come. Can you see the values? That shows that oxygen is more electronegative compared to chlorine. Oxygen is much more electronegative compared to bromine. Nitrogen is equal to that of the chlorine, but nitrogen is more electronegative compared to bromine. Right? So that's what I mean to tell. So not only halogens, we have oxygen and nitrogen, which are also more electronegative compared to some of the halogens. But no one will be equal to fluorine. No one will be equals to fluorine. So this concept is going to help you in redox reaction topic also. In redox reaction topic also. Anush, yes, normally it is applicable for covalent bonds. It is applicable for covalent bonds, not for ionic bond. Not for ionic bond. When I am talking about electronegativity definition. Okay? So naturally, those elements which is having high electronegativity, they will take up the electron. But there are some exceptional cases. I will come to that. But this one you have understood. So that's where we have the electronegativity. Even if you remove covalent bond, if you simply write bond, that is also fine. No doubt. Okay? It is the ability of the element to attract the electron towards its nucleus in a bond. That is also fine. But covalent bond, you are specifying. Okay? So that's where we have the electronegativity. That's where we have the Pauling scale. So which is having highest electronegativity in the periodic table? That will be fluorine. That will be fluorine. And alkali metals and all. When I am talking about electronegativity, alkali metals and all, they will be having least electronegativity, or they will not be considered as electronegative element at all. Fine? So what I mean to tell you is, if you observe the examples whatever I have given, inert gas we are not mentioning here. So whatever elements I have mentioned, if you observe it carefully, they are on the right side of the periodic table. They are on the right side of the periodic table. Right? All of you will agree? They are on the right side of the periodic table. Yes, Gaha. Absolutely correct. So therefore I can tell that electronegativity is going to increase across the period. Electronegativity of an element is going to increase across the period in rightward direction and will decrease down the group, increasing across the period and will decrease down the group. So sir, why not for ionic bond? See, when I am talking about ionic bond, see for example sodium and chlorine. Here they have become Na plus Cl minus. It is just an electrostatic interaction. Ionic bond is nothing but an electrostatic interaction. If I take individual molecule, ionic bond is a broad term where multiple Na plus Cl minus, they are interacting with each other, all together called as ionic bond. Right? Na plus Cl minus. That's how sodium chloride crystals will be there. Now due to multiple electrostatic interaction, now they have become a large force which are called as ionic bond. But as a single interaction, it is weak. If I take sodium chloride, if I add it to the water, easily they will dissociate as Na plus Cl minus. Right? So that's where we have the electrostatic interaction. Now how this Na plus has been formed? That is because completely donating the electron to the chlorine. It's completely donating the electron to the chlorine. It has lost the electron. Therefore it has become Na plus. It has gained the electron. Therefore it has become Cl minus. But when I was talking about water, I have not written positive. It is wrong. I had written delta positive. That means, delta negative. That means electron density is more towards the oxygen, but it is not having negative charge. It has not gained the electron. So here I had written delta positive. That means partial negative charge, partial positive charge. But here, positive charge, negative charge. There is no partial. Fine? So therefore, since ionic bond will be formed due to the complete donation of electron or complete acceptance of electron, electronegativity is not much applicable because there is no attraction, there is complete donation. Right? So therefore here attraction is important word, not gaining. So naturally it is majorly applicable for covalent bonds. It's majorly applicable for covalent bonds. Whether I am clear? All of you have understood? So that's where we have electronegativity. But 90% of the element, electronegativity and electron gaining, they will be matching. They will be overlapping with each other, but not universal. How? I will tell you. All of you have understood? In 90% of the cases, electronegativity and electron gaining, they will be overlapping. They will be having common features. But it's not universal. So don't think that electron gaining and electronegativity, they are one and all same. No. Okay? So in that case, anyway, I'll stop for today's class. What we have discussed today? So we have discussed what do you mean by atomic radius, ionic radius and van der Waals radius. Right? So in case of the atomic radius, we are going to consider covalent bond or metallic bond. Right? So van der Waals radius, majorly it is applicable for inert gas, which will be monoatomic in nature. That's where we are going to apply the van der Waals radius. Okay? Now, based on that, we can tell that in the rightward direction across the period, atomic radius is going to decrease. Downward, atomic radius is going to increase. Then we have discussed about electronegativity. So what do you mean by electronegativity? It is the ability of an element to attract the electrons in a covalent bond, where fluorine is going to dominate. With the Pauling scale, fluorine will be having value of somewhere around 4. And oxygen comes the next, 3.5. Then chlorine and nitrogen, 3. Then comes the other elements, halogens. Right? So metals will be having least Pauling scale value, no doubt. Okay? That comes under electropositivity, electropositive element, which I am going to discuss in the tomorrow's class. So what is the relation between electronegativity and atomic size? Yes, I will conclude the class by relation between electronegativity and atomic radius or atomic size. How to relate between these two? We can relate that electronegativity, I will mention it as En, is inversely proportional to atomic size or atomic radius. Right? Because as you are moving towards the rightward direction in the periodic table, atomic size is going to decrease, but electronegativity is getting increased. So that's where they are inversely related. Try to remember this equation. Electronegativity and atomic size or atomic radius, they are inversely related to each other. In the period, across the period, atomic radius is going to decrease, electronegativity is going to increase. Down the group, atomic radius is going to increase, electronegativity is going to decrease. So they have inverse relation. So try to remember this equation. That's what I will conclude the class by this particular equation. Fine? Okay? So any doubts in today's class? Another doubt is there? Oh, some picture is there. Thank you, sir. Mansi. What is that blue shaded? Oh, chemistry, like that? Okay, I was simply making fun. Don't worry. Thank you. Thank you, everyone. Take care. Okay. Bye.